this booth explains a little more technical details of the exploration procedures which have already been presented in the last talk today in the session 4. And I will present both procedures also on behalf of my colleague Barbara Schütt, who has designed and implemented one of these procedures. The common problem is that we are given a logical scenario with some parameters, and we want to explore all of the concrete instances of this scenario to look for critical instances. Okay, and there are two procedures. One which tries to find interesting points, critical instances fast, and the other tries to provide also a guarantee that nothing has been overlooked. And the first procedure goes in a loop by choosing some sample points for simulation and evaluating these simulation results which have been achieved, then choosing new, better points which give us a handle on the potentially critical situations which might evolve. So, start from some points, evaluate the results, and in a clever way choose new simulation points to perform and evaluate and so on until criticalities have been identified. This is, come to the bottom of this poster. This is an instance of the well-known method of base optimization, where from the known points, little points in red, the unknown target function, the criticality function on the scenario space, is estimated from the already performed simulations. We extrapolate the results, and we see here the red extrapolation function with a confidence corridor around it. And the more points we get in the simulation, the more points we have already done, the better gets the extrapolation, of course. And in the end, by this way of having these extrapolations and as a basis for choosing new points to simulate, we are able to find interesting points very fast. This is, in other respects, explained in more detail in the talk, which you can also see. So one can say that one can achieve a factor of speed up of several thousand and still get to the interesting points in some experiments which have been performed. Now, on the right side of the poster, we see, well, a slightly different question, which is addressed by a different procedure. Namely, we want to find all the critical points. These are the little red areas here. We want to find all of them and cover them and be sure that nothing red has been overlooked in the vast blue sea of uninteresting evolutions of a scenario. We want to make sure that every point which should be analyzed closely is indeed identified. So, and this is then done, identified by representative simulation routes, which tell us in a local neighborhood, okay, we find critical ones, or green circle uncritical ones. We start by making the problem, say, a little bit simpler than it might be in the beginning. Namely, we make our criticality indicator a continuous function on the trajectory space. In that, we don't want to have these jumps in criticality when, for instance, car changes lanes, and we see here the time headway is long between the red vehicle and the green one, And once the blue one enters here, it jumps from uncritical to highly critical. That is a behavior we don't want of our criticality indicator, by saying, okay, once it is already close to the right lane, it should indicate there's a small step to high criticality. So criticality indicator should say this is already one before entering the lane. This is a point of significant criticality. So we can do that. We can make a smooth, continuous criticality indicator out of each criticality indicator we are given by standard mathematical means. Now, there remains one source of discontinuity, namely in the parameter space, where, for instance, if our car turns right somewhere and there's a pedestrian crossing the street, there are three outcomes. The car passes before the pedestrian, the car brakes and let the pedestrian pass, or one thing we don't want to have is the car hits the pedestrian. But between waiting for the pedestrian and passing before, this is influenced by the parameter combinations, and there will be a switch, an abrupt change of behavior with a minimal change of parameters. These we have to identify. These are the black and red lines. These are identified, the green ones, the inside of all these discontinuities, where we have a continuous region. And such a continuous region, coming to the last picture, we can then cover by local neighborhoods for the blue ones and also for the red instances, for the critical instances. This is the idea of a procedure which can give some kind of guarantee that nothing has been overlooked, because everything has been covered, and we know that there will not be any criticality outside of our covered set. So, more detail again in the slides and in papers which are referenced there. Thank you very much.